today we are at AC/DC microgrid and its application. And I'm very sure some of you might have listened to me in the past. So please don't get bored about my content. I will see to that I can certainly bring some innovation in the next couple of months. Just to start with, because I could see that there are so many faculty colleagues, and some of them may not be aware about what is smart grid, and they're very curious to know. So to me, the basic architecture of any power system. Rajiv, am I audible, loud and clear?
Yes, sir.
Okay, so please interrupt me if I'm not audible at any.
Okay, definitely.
Sure. So, when you look at the power system, I mean, it's a very basic structure of the generation, transmission, distribution. And, anytime when I question myself for the last 10 years, when I'm working on microgrid, you see, the power network is not going to change. All of you, please try to understand this concept. The generation centers will be as it is. The transmission networks will be as it is. The distribution substation transformers are not going to change. The consumers are not going to change. So then, what is microgrid? Now, what is smart grid? What is microgrid? There are a couple of things which are going to change. The way the distribution system is expected to operate is going to change. Okay? And the consumer behavior, which is going to change. The flexibility on my generation power plant is going to change. Okay? I will give you a very simple example to start with. Now, in the past, all the thermal generators are expected to operate with its maximum capacity. So once switched on, it will be on for a very long time. And a 100 megawatt power plant will operate almost at 95 to 100 megawatt. And that is how we operate. But today, because of the new installation of renewable generations, for an example, solar, now during the daytime, sometimes, not all the time, during the off-peak hours, my solution or my generations from renewable technology may be quite enough to meet my consumers' loads. And hence, I have to ramp down my thermal generators little bit. Okay, please try to understand, take your pen and paper, please write it down. It's very interesting. So when the thermal generator has to ramp down its capacity, so then, which is not acceptable. In the past, it is not allowed. Thermal generators, once switched on, they are forced to switch on forever. They are forced to operate with its maximum capacity as much as possible. But today, the scenario is not that. Means the generator is there, the power plant is there, but its operational behavior, the flexibility on its operation, ramping up and down characteristic got changed because of solar PV or maybe wind generators. So to me, smart grid means what? I mean, the generation has not changed, the power plant has not changed, but its behavior actually got changed. Similarly, when I'm putting an electric vehicle on my distribution system or my house, or to be very easy to understand, the electric rickshaws, today we see millions of electric rickshaws. So what they are doing today, they simply charge the vehicle and then they go to field for carrying the customers or goods. But there is no pattern attached to that. So the smart grid is expected to follow certain patterns, certain procedural things, where we can efficiently engage our renewable generation to its optimal use. Okay. So if I try to charge my electric vehicle when the energy available to me is in excess, or indirectly I am at off-peak period, or I am at a frequency of 50.05 for an example, and that time I'm supposed to charge my electric vehicle, not any given point of time, the way we are doing it today. So the electric vehicle is there, but its behavior is expected to change because of smart grid. So to me, smart grid means it is the existing power system with more infrastructures and maximum flexibility and optimal utilization of resources Okay, and that is what actually to be known as microgrid, and probably all these things can be achieved at a low voltage level, and hence we call it is smart grid or microgrid for distribution systems. Okay, so my dear friends, don't get worried. Don't feel it is something very big thing or new things or altogether different thing. It is exactly same electrical engineering that we have learned in the past, but with all new inventions, new technologies. So how do you fit into that become a challenge? Okay. All right. So quickly, as you all know that we have different EHP AC systems at different kV levels, like 765 to 800 kV, the highest voltage level. Then we have 400 to 2132. But all our smart grid operations, microgrid operations, normally we perform below 33 or 11 kV. So that is very interesting. Now, when you talk about electrical grid component, so when we all were, when I was young especially, but I don't know about your time, we have been taught that, there are two types of sources. One is hydropower plants, and the other one is going to be thermal power. All the textbooks we have read, that also speaks about this. But today the storyline got changed. I mean, we have introduced a new term, is known as RES, renewable energy sources. So that is what the new story comes to action. And there are previously we had two type of transmission system, HVAC, but today we are talking about HVDC as well as in transmission system. But in the distribution system, we have had actually AC systems, but today people are talking about DC systems, DC microgrids, AC DC. So these are all new terms. Okay, so let us see why we are talking about. And the consumers remain same. In the past, we had a vertical integrated system, but now we are actually looking at restructured systems. So first I will talk about Indian power system, then I'll talk about smart modern power systems, and then smart grid. So when you talk about very quickly, so about the Indian power systems, I think most of you may be knowing it, but still I am very, once again happy to share this thought process. In 1960s, we had grid based on regional basis. And we all know that there are five regions for Indian grid, such as northern, eastern, western, northeastern, and southern regions. And one thing is very clear that we first time we have integrated two zones, northeastern and eastern zone. And slowly in March we entered the western zone to be integrated. In August, actually, North got integrated, and finally, the Southern grid integrated in 13. So from 2013 onwards, we are talking about one grid, one nation. Okay, and now people are talking about one sun, one world. Okay, so I'm just waiting for the day, maybe 2025 or 2030 or 2050, how the country will operate as one sun and one world. Okay, so. But anyway, certainly it is possible. Let's see how it is going to evolve. Now, even if you see the contribution from each component, one thing is very clear. The renewable contribution today is close to 25%. Renewable contribution is going to be 25%. But here, something I like to highlight here that most of us might not have realized. Today in a thumb rule, the installation capacity is close to 400 gigawatt. I do not want to say 390, 389. Let us say it is 400 gigawatt. So when the installation capacity is 400 gigawatt, what is our peak requirement every day? I mean, you can just type your numbers in the chat box if you are comfortable. But one thing is for sure that the peak requirement of this country is close to 160 to 170 gigawatts. Okay? Not during pandemic, but in a normal year, okay, a normal regular date. So my important question to you all, that when we have installation capacity of 400 gigawatt, and the peak requirement is actually 170 gigawatt per megawatt, why do we experience power cut and peak energy deficit? Any clue? Here I like to spend a little bit because of all faculty colleagues. Can anyone please unmute, not in a mass, anyone at least, and tell me, having 400 gigawatt of installation capacity, having 170 gigawatt of peak requirement every day in the evening, still, why do we experience power cut? Anyone will come. And what we can do, Rajiv, maybe just to help our audience, maybe we too can, okay, I'm getting some answers. There is a fault in the transmission line. Okay, only because of fault, that means every day of the year, we are experiencing power faults or something like that, transmission line fault distribution.
Renewable energy.
Anji?
Maybe intermittency nature of renewable solar.
Okay, I mean, it's okay. You are very close. This is good. Okay, one question. Anything else? I'm very happy that, you know, this, my participants are so reactive and I'm getting 100 of some theft of power. Oh, no,
Sir,
no.
sir, to generate economy, sir.
All right. Okay, let me answer. Amit also has come. Okay. So very good. I mean, most of the names are known to me, at least half of them. So I'm very happy that, you know, it's wonderful. So let me say, okay, you just chill out, just cool down. Okay. You can just mute your speaker now. Always, I used to tell one thing to my students, my scholars, and even in during talks, one statement which is very popular, and you must have also heard, that God is not kind to engineers. Okay? God is not kind to engineers. You all agree, Rajiv? आप agree कर रहे हो?
Yes, sir.
अरे इसे डर के मत हाँ करो यार actually.
No, sir, actually it was unmuted, so.
Yeah. So, I mean, in a sportive sense, don't take it otherwise. I mean, God is kind to everyone, but especially God is not kind to engineer in a sense. God has given you sunlight. God has given you enough wind. God has, you know, given a lot of natural resources. But you see, with the unfortunate part, He has given you wind, okay, and the wind blows the maximum, and maximum wind energy is available to us during midnight. Maximum wind power energy available across the globe is during night hours. And night hours, we all are sleeping. So, I mean, I really do not want anything to happen. So what has happened? He has given me the sources, but not given me at a time when I need the most. When I need the most, I need the most at 6 to 7 p.m., the evening peak. Okay. And similarly, God has given me enough sun to utilize my rooftop solar or maybe PV solar. But they are also again available to me before 7 p.m. So what has happened? God has given you two baskets, but both the baskets are available to you when you do not need them. So now the engineering begins, you know. Now the engineering begins. That means He has shown you some attraction. Okay, it is there for you. But how to drag that to 7 p.m. is your challenge. So that's what we are talking about, storage technology, the renewable energy to be stored and discharged as and when required. We are talking about actually demand response of electric vehicles. You charge the vehicle when it is available to you, not as per your choice. Go to the petrol pump, put the petrol and ride. No, you go to the petrol pump or maybe a charging station at 10 a.m. and if you are supposed to start your ride at 4 p.m. So that means, you know, these are all engineering, you know. So God is not kind to the engineers means God wanted engineer to be more innovative, more creative over a period of time. They should not really relax and they have no time to sleep. That's what I could say. All right. So that's my intention of saying that God is not very kind to you. So now coming back to the original question that I have thrown. So now the answer is clear. Because the 400 gigawatt of installation capacity, because of intermittency, they're available to you at different pockets of the day or different durations of the day. So when I talk about peak, that peak happens at 170. gigawatt during 7 p.m. for an example, when none of the wind is there for you and none of the solar is there for you, okay? And hydro powers, they may be operating with 40% efficiency for an example during summer, and thermal power plants may be operating with 80 to 85%. So if you take the mixture, I may be left out with 165 gigawatt. And hence, 5 gigawatt of shortage being experienced by Indian utility at 7 p.m. My dear friends, try to understand. And that's known as peak energy deficit. So even having 400 gigawatt of installation, I experience 1% of peak energy deficit at 7 p.m. on a particular day or month of a year, so that we experience a shortage of power or power cut, excluding transmission failure, distribution transformer failure. They're all rare cases. Okay? So now, but one good thing happened over a period of time, that the peak energy, which was almost 3 to 5% before 10 years, and today it is less than 1%. Okay, because why it is happening? We have put so much of new generations, but the consumers also started using more devices. They had one AC in the past, today they're using 2 air conditioners. Earlier we had actually 1 laptop, now we have actually 2 laptops. Earlier actually we had bit of comfort, now we want full of comfort. So the consumption pattern also increased. So now the question is to overcome the peak energy deficit, and if you wish each Indian citizen not to experience power cut and celebrate Diwali almost every year, what we need to do? We have to increase our generation. When the requirement is 170, my installation capacity has to be 425. So that 5 gigawatt of shortage that I experience can be overcome. Okay, assuming there is no change in load. So what I'm saying, at a given point of time, at one yardstick, there is no load increase, but there is a generation increase of 20 to 25 gigawatt, so that India will not experience any power shortage, or all the villagers must get power all the day. All right. So what we need to do, what is the immediate question in front of us? Smart grid is fine, but first step will be, we have to put lot of installation capacity in this company. And to put that installation capacity, if you go for a thermal energy or a nuclear energy, or if you go for hydro energy, you need 7 to 10 years time. Theoretically 3 to 5 years, but reality is 7 to 10 years. And which is, we don't have time. By the time you really bring the generator, the shortage might have gone to 5 to 7%. So what is the only source India has at this point of time is to put a lot of solar and wind, which can happen within 6 months to 1 year. These are the generations which can put immediately. And that's why Indian government become aggressive for last 5 to 7 years to go for excessive solar and wind, or so-called renewable energy. And now, because we have gone for renewable energy, they are actually intermittent. So we need to have little bit of shifting of loads, little bit of storage technology need to be brought in. Okay, and loads, electric vehicle loads which are coming up in the future, they must be engaged when the generation is plentifully available. So through this process, actually we need to manage the distribution system optimally. And that is only possible when the distribution system is reasonably smart. All right. And that's the beginning of smart grid technology. That's the beginning of smart grid technology. I'm a bit proud here to say that, IIT Roorkee got the first smart grid project in this country in the year 2012, where when we really never knew what is smart grid before 10 years. But that project becomes so successful in a demonstration testbed level. And today almost you talk to any electrical engineer, they know what is smart grid is all about. So with this note, let me move to the next one. I hope my dear friends are able to catch up the background. So once you know the background, then it is very easy to follow further. Okay. So Rajiv, is it clear the background story of why we are into smart grid?
Yes, sir. And you have explained it in a very simple and decent way, sir.
Thank you. Thank you. So, I mean, this is the storyline, we are predicting actually because it's a very long backstory. So, if you see the yellow line, which was hydro, the hydro is not going to increase and it's almost going to be steady because there are a lot of political issues, environmental issues for hydropower projects. So, hydropower project is not going to grow much. Whereas the PV, you could see that it is exponentially increasing. Okay, and also wind is also expected to increase very significantly. Now, this is one slide, I like to present in front of you, and perhaps I like to acknowledge Professor S.C. Srivastav from IIT Kanpur, who has helped me to prepare some of this PPT. So, what I thought that, in one slide, how can I really explain the whole Indian power system to my fellow colleagues? So that was the thought process. So this one slide is whole India, and this slide is not common to international different nations. So what exactly happens? All of you, please try to understand. And most of my own graduate students even do not understand. They work on smart grid, but they do not know who is controlling what is happening at national level, who is forwarding the rules, who is implementing. So one has to really know it. So we have central government at the center, that is Ministry of Power. Okay. And then all the state governments actually follow these rules from time to time. Okay. And there are different generating utilities, transmission utilities, system operators, finances, and rural electrification. Very importantly, the system operations like NLDC and RLDC are controlled by POSOCO. Then we have Power Grid as a transmission owner. Then we have NIPCO, NPCIL, NHPC, NTPC. They are the generating utilities. Then we have authorities like CA and RPC. Then we have R&D institutions like CPRI, NPTI, PSTA. Then we have independent power producers. And there is the appellate tribunal who settle down some of the differences. There is a regulator who are CRC. We have two power exchanges, IX, PXIL. The third one is in process. The regulator SCRC. And then you have state-owned generation, transmission, distribution, and then we have trading companies. So that is how the whole business goes every day. Now, this is where I like to spend some time. So this is in public domain. Now, what happens? The beauty of Indian power sector is that the whole world should learn from Indian power sector. Many countries thought about deregulation in recent times, maybe 2 decades old problem. But India was deregulated almost for last 30, 40 years. So we had the independent states, like Uttar Pradesh State Electricity Board, Tamil Nadu State Electricity Board, Odisha State Electricity Board, Bihar State Electricity Board. So that means what? We have been, working like a deregulated power industry for a very, very long time. But somehow actually we could not project to the world that we are the best power system in the country. But nevertheless, now there is a lesson to all of us. All of you, please have a look from the matrix which is presented in front of you in the right side, though it is a very old data, but this is very scientific. If you look at the renewable energy contribution, which region do have the maximum renewable contribution? Any one of you?
Sir, wind energy.
No. Which region? Southern, western, northern?
Sir, southern region.
Very. And what is the installation capacity of the southern region? Close to 100 gigawatt. Okay. Close to 100 gigawatt. And the renewable energy source is close to 35. So what does it mean to be? It means 35% of energy can come from renewable by making the system stable without collapsing. Okay. So there is a common question that comes to our mind. What percentage of renewable that Indian power system can tolerate? Is it 10%, 20%, 30%, 50%? People are talking about 100% today. So one thing for sure, that 35% of renewable can easily be accommodated in this country. So if I say my installation is 400, 140 gigawatt can come from renewable. Am I audible? Someone is saying I'm not audible, Rajiv, can you?
Sir, you are audible.
Yeah, maybe some problem with his technical. Okay. So 35% will be, audible. I mean, 35% will be renewable. Okay. So if someone asks you, or if you are doing some research and if you are not convinced what percentage will be the right figure, I think we have the answer in front of us. 35% will be the easy guess to start with. That 35% of your network generation can come from renewable. Okay, and within 35%, the mix of solar and wind, that is up to you. You can at least consider 50-50. Okay, so that's my call. And someone asks you what would be the percentage of renewable after 10 years and 15 years. I'm very sure it will be more than 35 and can be close to 40%. But beyond 40%, I'm not very convinced in this country because of one reason. The transmission network planning that we have done in the past has been carried out without thinking that so much of renewable energy can come to my network. Okay, that's the problem the southern grid is facing today. If you look at Tamil Nadu, the load centers and the renewable energy centers are 500 kilometers apart. So in the past, it has been planned that all the energy will go from Madras to Madurai. But today, during some time or during the peak renewable, the energy is coming from the coastal of the southern part towards the northern side of the southern states. So that means the scenario is changed. So the network is not designed to evacuate all my renewable energies which are coming up in pockets, and for which the transmission network has not been planned. So now we are planning a green corridor, especially for tapping the renewable energies. Okay, and someone is saying that in 2050 we will have 100% renewable. My dear friend, that is true for some of the small European countries, but I am for sure this is not true for Indian context. Okay, because the geography and the based on and because of because of the geography and as well as looking into the energy mix, I am not very sure that we can shift to 100% renewable, and that is not possible because of the distance. Like country like Denmark, they can preferably operate with 100% wind energy possible, but Indian context it is not possible because how to get the inertia, that is the bigger question. Who will stabilize my network? That is the second question. And what about the storage technology? Who will manage the scraps and who will replace? The technology is not belongs to ours. So considering everything, to me, 40% is a very good number. And if we can, achieve 50, 60, that is wonderful. I'm not a very optimistic person in the sense 100% renewable for research, it is fine. For understanding, it is fine. But it's better to say we will increase the renewable penetration in our Indian grid as maximum as possible, but not saying it is complete. Okay, very good. Now, and hence we are slowly moving to a Indian power system. There are a few things which are like, very, very surprising. All of you, please have a look. Now, Indian distribution system caters 400 gigawatt of load over 200 millions of customers using 73 distribution utilities. Can you imagine any distribution system in this world will be so complex as we are? Okay, so it is not easy. And the very unfortunate part, this is the only country which experienced more than 20% of transmission and distribution losses. Just now I told you that 1% of energy deficit, and if you could reduce 1% of losses, then certainly you can work. But one good thing happened, that because of renewable energy, they're very close to the distribution network. very close to the consumer end. And hence, I'm very sure that if you can, because of renewable integration, it is not helping you for quick installation, but it is indirectly helping you for the reduction in the distribution losses also. Okay, so I think this is one of the greatest challenge we have to face. And now the renewable energy share is close to 16 to 20%, and this share will go as high as 40%. Okay, so this is my thumb rule. I mean, please, don't take it to public saying that Padhy साहब कह रहे 40% होना चाहिए. ऐसे नहीं है. But one thing is sure, actually, every year, whatever I do predict, and that is somehow actually, going closer as per the development, we see. So I'm very sure in a couple of years from now, maybe 5 years from now, we will have actually 35% of renewable. And 10 years from now, we'll have 40%. Yeah. So the biggest challenge what we have is the forecasting tools. Okay, so any microgrid to operate, we need to have wonderful forecasting tools. We need to have wonderful forecasting tools, because if you do not predict, then you are in trouble. And we are also using the same latest software what international community is using. But why do we experience forecast errors in this country? Because of the geography. So the geography at which we are placed, none of the commercial software can guarantee the forecasting. So if you are really looking for some innovation research at your end, please focus on renewable energy forecasting, renewable energy forecasting. So that is where India needs a lot of power engineers to forecast the renewable energy. Forecasting for wind and solar is very important, because of the geography at which we are situated. No conventional algorithm present in the market today can help you with 0% error. Okay, so that is what my suggestion. So what is the challenge in front of you today? To me, there are two challenges. One is losses are higher. So control is minimal as renewable integration is minimal. So we need to have optimal control mechanisms, reduce losses. So the future will be large renewable penetration, right? To increase the renewable penetration to the maximum extent possible, and then have wonderful control mechanism to use them. And losses can be managed and reduced further by both optimization as well as due to renewable technology. So the future will be maximum renewable, minimum loss, and better control mechanism. So these three, when we put within any smart grid environment. So when you come to a point, so there are 10 research problems in front of you, because you all are faculty colleagues. Rajiv, all are faculty colleagues here, or any students are part of this program?
Sir, a few students are also there, but most of them are faculty.
Yeah, and some of them might have done PhD, and some of them working on PhD. Okay.
Yes, sir. Yes,
So
sir.
I have identified 10 research problems for them, so that their PhD can be completed successfully. So one problem they can work on, the demand matching. There is an increase in demand. Keep on, we are running behind the demand. So how to catch up? So all the time we have peak energy deficit. We are all the time have power failures. I mean, how to really manage it? So that is one problem, demand side. Just give me 1 second. Just give me 1 second. There is a call, urgent call. Just give me 1 second. Keep. Yeah. Am I audible now, Rajiv?
Yes, sir.
Okay, good. So the second problem is supply shortfall of electricity. Means how to, if you have 400 gigawatt, try to have the maximum percentage of energy availability. And third problem is reducing the losses. And there is a problem with my conventional power plant today, all my thermal power plants are not operating with its maximum capacity. And then one more point is actually peak demand management, So how to reduce my peak, and where your electric vehicle, the theme of this FDB, come to action. Electric vehicles in this country only can help to reduce my peak energy requirement. Okay. And then integration issues, integration challenges with renewable energy. And then effective use of electric vehicles in demand response programs. Then there is a smart meter issue. I mean, SCADA system, meter reading, smart meter data. I mean, all these things are very important. So that is another area one can work on. And few business models, distribution system operator, DSO, market, which are not there in this country, how to really work on these areas. And finally, the reliability and customer satisfaction. Okay, so these are the 10 problems open to you, my dear friends. Though I've not told you any technicality about these problems, but one thing is for sure, if you you can capture any one of these area, and all these 10 problems belongs to your smart grid applications. All these 10 problems can be solved using smart grid technology. Now we will move to how those 10 problems can be answered. And the first is going to be smart grid. So we are slowly entering to smart grid. And if you like to address those previously mentioned 10 problems, then we need to have a smart grid technology. But one information you all should know, electrical engineering, which is a 200 years old problem, and the smart grid is a 10 years old problem. So for the first time in the history of this country, 2010, we had a smart grid task force established. So one way I'm very, very happy, the way India has grown on smart grid today is very, very remarkable. In 10 years time, we have thousands of publications, hundreds of patents, millions of students, and thousands of PhDs, and hundreds of FDP programs. Okay, so I'm very sure that we are really aggressive, and we can certainly rule this world on the field of smart grid. So then we established Smart Grid Forum in 2010 and NSGM in 2015. So, it is also equally important for us that, when you talk about research, smart grid research is something different. Smart grid research is something different compared to your conventional research. Smart grid research is not possible without having reasonable hardware setups or hardware testbeds. Okay? And to do that, we need a lot of funding, and that funding can come from different sources. So I have prepared a small graphics for you where to approach for your fundings. And again, Rajiv, because so most of the faculty colleagues are crazy, to have some research funding, and it would be a nice idea to help them actually where do they approach. They're really confused.
Yes,
how
sir.
to get the funding and what needs to be done. So is it a good idea? Also, not necessarily tell them 10 research problems, but also tell them that where do they get some funding to do their research. Okay. So will we continue or skip this slide?
Sir, we can continue, sir.
Yeah. So first one, you can go to DST and Department of Science and Technology. So they have three verticals, three pillars. So one is SERI, Clean Energy Research Initiative. We can go for International Collaborative Project vertical, or you can go for Incubation Center. And further, there is one thing called as Mission Innovation, on which Dalbag is working, IIT Roorkee is working. All right. So, and then in the mission, then we have another collaborative program called Indo-UK collaborative, and I'm very happy that IIT Roorkee is also working on this. And then we have Indo-US collaborative programs, and then we have Indo-Dutch, Indo-German, and then we have Ministry of HRD. You can try for Imprint or UAY, which is Uchatar Aviskar Yojana, Energy Track. Then we can go for MITI. MITI is talking about actually cyber applications, cyber physical application on smart grid. And then you can go to Ministry of Power, and there's a lot of pilots, large projects. You can get crores of funding from Ministry of Power. And then finally, you can also go to different sort of thing to talk about synchrophasor applications. And so these are all available and a lot of scope actually in the smart grid research. So I request all of you, so please collaborate with different institutions and trying to claim for some funding, create some infrastructure at your institution level, and then do good research and complete your PhD successfully. So when you talk about making a grid smarter, I will not take a lot of time. So to my understanding, in the past, actually, it is one side. So, the generation company or, used to detect whether I'm eligible to get electricity or not. It's a one-way communication. But today, I can have my own generation. I can sell my generation to a generation company. So that is what smart to me. And a wonderful communication which has been established between generation and load, which was not there in the past. And because of this, I can call my distribution system become smart when I can communicate with my utility. When I can communicate with my utility through any form, through be a cheaper electricity availability or discharging my actually, storage as and when required, or not to draw power from the main grid. So if you can communicate with your utility, I will call my distribution system is very, very smart. So there are different definitions from European side, from US side, okay, about the smart grid communication. But there are few standard definitions. 2006, it has come from European grids. And if you see, almost everyone speaks the same language, what I told you just now. A smart grid is an electricity network that can intelligently integrate the action of all users connected to it, generators, consumers, and those that do both, in order to efficiently deliver sustainable, economic, and secure electricity supplies. A smart grid employs innovative products and services together with intelligent monitoring, control, communication, and self-healing technologies. Okay, so this talks to the whole story, but just to start with, a communication, exchange of information, okay, and then further action to benefit the whole distribution system, and that infrastructure is known as smart grid infrastructure. Okay, so please, and there is also a few more definitions by Department of Energy. This is also a very interesting definition, very brief. They call grid 2030. So they pre-assume that 2030 whole world will be, smart, but they have created this definition in 2020 before, 10, 15 years back. So they never realized that, but I doubt actually when in 2030 we can be completely smart, not possible. So they visualize that a fully automated power system delivery network will be available to them in 2030, which will monitor and control every customer. Okay, control every customer and node, ensuring two-way flow of information and electricity. Okay, and once that has been established, your network has to be smart. Okay, so if I can, share my thought process to the utility, and utility can control my load based on my agreement, and then I can say my distribution system is completely smarter. All right, so now one important thing, let me quickly get into the application. And, is it a good idea, Rajiv, that we also explain some application to our fellow friends so that they know actually,
Yes, that would be good, sir.
Yeah, because
if they are planning for the not only for the teaching, if they are planning for the fund for the research projects or industrial collaboration like consultants, etc., that will be good if they will know the applications of it.
correct. So what we are, kind of suggesting here is that let me get into a few applications quickly instead of getting into the theories, because you can also refer to my video lectures to understand more about theory. So first of all, what I talked about a typical AC microgrid. So typical AC microgrid means it is basically a simple distribution system. Don't feel it is very tough. But one thing is there is a point of common coupling, okay, where all my loads and generations, renewable generations, electric vehicles, what not, they are connected. and you have a single blue line AC grid. Now in this AC grid, you can have micro turbines, you can have fuel cells, we can have batteries, we can have wind generations, we can have electric vehicles, we can have PV solar, as well as DC-AC loads. Okay, the sources could be of any type, but the whole system will operate on a common grid coupling. Now, the important part, what we experience, before I go there, I like to give a wonderful example before you understand it fully. Now, I will try with my IIT Roorkee campus grid. IIT Roorkee, all of you please take your pen and paper, note it down and try to understand so that you can apply to your own campuses, own microgrids. Now, ours is actually close to 7 to 8 megawatt of actually requirement, power requirement, the peak requirements. And we have approximately 1.8 megawatt of actually solar. That's 1.8 megawatt. And planning to add 1 megawatt in next 1 month. So we will be having 2.8 megawatt. 2.8 megawatt solar. So what is the percentage? 3 out of 7 megawatt. 2.8 megawatt out of 7 megawatt. What is the percentage? 40% of the total installation is my solar. Okay. And now can you connect actually why I told 40 in the past and why my campus also have 40? So our campus actually we made it as a realistic microgrid, not a theoretical method. Okay. So we are putting 40% of solar, as the maximum renewable that India could experience in this grid. Okay. And then we have 100% diesel generator, means diesel generator of 7 megawatt. If there is some failure, whole campus can be supplied by the diesel generator. And then we have the uninterrupted grid. We have a wonderful grid. So almost there is no interruption. We do have grid. Now the biggest challenge here, if the grid is not available to me, then my 2.8 megawatt of solar generation actually stops. They don't generate because they miss the reference point. Now that's why we need to think of, if you increase excessive renewable energy to the grid, it is fine. But can we operate in both islanded and grid integrated mode comfortably and efficiently? And typically, if you can, that is a perfect AC microgrid. Now, so we can have two different type of operations. Either it could be a grid connected or it could be a islanded mode of operation, and different type of control schemes actually you can exercise. But now the biggest problem what we see, because the renewable powers, they come through DC and then I convert to AC. So there is a question, why not the majority of the DC loads are connected to my DC sources? Okay. So probably I can have a DC-DC converter and then connect all my DC loads, especially the heaters of the messes or the computational labs of different departments can be connected to my DC grid. So what is happening today? Each department of IIT Roorkee do have approximately 200 kilowatt of load and 150 kilowatt of actually rooftop solar. So the target here, if I can use my rooftop solar directly connected to my computational labs, which can operate easily with DC loads, DC supply, then probably we can save a bit of energy there. It's an R&D thought process. Or the UPS systems, if you can charge directly by the rooftop solar itself. Okay. So now we are proposing that not all, but at least a selective electrical engineering department can have actually both DC and AC grid. All right. And then try to understand the phenomena of AC-DC microgrid. And I'm also very happy to say that we are having 274 kilowatt of battery, lithium-ion battery present within electrical engineering department. Okay. And maybe, I can take maximum up to 200 kilowatt out of it at a given point of time, assuming 80% SOC. And then my load will be, let's say, 250 kilowatt at a given time during the lab hours. And so 200 kilowatt I can take from storage and 50 I can take from actually my solar power plants or maybe from the main grid. So the electrical engineering department today is a wonderful microgrid to me in a campus distribution system where I have storage, where I have DC loads, I have AC loads, I have renewable solar, I have the main grid integrated. But prior to do that, it is not easy, my dear friends. Please do not connect 200 kilowatt of storage directly to your grid. It's a big disaster. So to do that, prior to that, actually what we have done, we have played with actually a 5 to 25 kilowatt of storage, a 25 kilowatt system with some storage, some renewable, and the main. And we have experimented, we have created a test bed with power hardware in loop simulation, where we experience certain challenges. And then slowly we are uplifting the capacity 5 to 10, 10 kilowatt to 20, 20 to 25. And perhaps in a month time from now, we will be able to connect 270 kilowatt of storage. And there is also a serious plan that already the order is in place. So if everything goes normal, in next 6 months time, IIT Roorkee campus will have 800 kilowatt of solar at 5 different pockets in the campus. So we'll have a distribution system of 7 kilowatt, 7 megawatt with 800 kilowatt, 5 microgrid clusters operating within the campus. So by doing so, even the community microgrid concept can be exercised as a research point of view. Okay, and then this technology can go to the field for multiple deployment. So, but it took a lot of time. Just I'm telling you because what we have experienced, I'm telling you exactly the same thing in front of you. So we have a operational test bed today of close to 15 to 20 kilowatt, which is functional, which is operational, which has been integrated to the distribution system of 7 megawatt. And we have storage technology in place, and probably you can also experience at your level. So assuming all this application, there is a question, why not we move to DC microgrids? Okay, and that has actually forced us in the past, even today, that we need to go for both technologies, that is a DC microgrid as well as AC microgrid. So we can have a DC bus, we can have a AC bus, and DC bus we are experimenting at 1 voltage level, that is 48 volt. But few researchers are suggesting you can also go for 380 volt for better use of cable sizing and other things. But I'm a bit nervous with 380 volt DC, how safe it is for my researchers to experience such new innovations. Rajiv?
Yes, sir.
380 volt DC, is it safe?
With the insulation, sir, actually, I think this is the equivalent of the, approximately equivalent of the present distribution system for the buildings.
It is slightly more actually,
Yes, that will be 325.
Mm-hmm.
Yeah.
And the transient is issue actually.
Yeah, the switching is the,
and switching, and then the protection for 380 volt DC. That is another challenge. And any spark, I mean, we are worried. So we are experimenting with 48 volt only today.
Yes,
but probably one can think of 300 plus volt also with proper insulation and proper cabling size.
yes,
The
sir.
biggest advantage is the cable size will reduce if you operate with 300 plus volt.
Yes, sir.
So we are convinced that DC microgrid is also an important, AC microgrid is also an important issue. So why not operate? Because you cannot only survive with DC microgrid, that is for sure. But you can add DC microgrid to AC microgrid to have the better merits from both the sides. So the conclusion will be one should work on AC DC hybrid microgrids for the utilizing the best out of both the components. And you can also think of different type of control mechanism. One could be decentralized control, distributed control, centralized control, and finally you can apply group control mechanism, voltage leveling, and DC bus signaling And finally, all of you please note it down that root control, which is a very basic control mechanism, one is to adapt in both DC microgrid and AC microgrid. But the biggest challenge is we do not have frequency in case of your DC microgrid. Okay. So that's where actually you have to utilize your PNB, real power PNB, to utilize your group control mechanism. And once you achieve that, then AC/DC microgrid operation in a real-time simulation platform is very, very easy. And so that's what actually it is good to have both AC and DC. And not only AC, not only DC, but the combined will be a better option. And the title of my today's talk, AC/DC microgrid, is being justified at this stage. One important is that, the common bus, which is both AC and DC, and the hybrid microgrid is connected to the utility grid for excess and deficit power sharing and for increasing the reliability of the. So in case of main grid fails, all the connections and loads can communicate in both AC and DC power platforms. It is a combination of AC/DC microgrid to be named as hybrid microgrid. So finally, the hybrid microgrid will look like this. And you could see I have taken this diagram from a source, which is very nicely presented in 2015, Nizam Padhy. And you could see there is a DC bus, there is a AC bus, and then we have interlinking converters in between those two. And all the sources can be connected to AC bus. All the sources can be connected to DC bus. And both AC and DC load can be either connected to DC bus or AC bus. Okay. So my suggestion to all of you, if you are really building a test bed, please focus on AC microgrid, then move to DC microgrid, then plan for AC/DC microgrid. Okay. At IIT Roorkee Smart Grid Laboratory, what we have done, we have created a AC microgrid of close to 15 kilowatt capability, and a DC microgrid close to 4 into 13.5 kilowatt, and total AC/DC microgrid capacity is close to 28 kilowatt. Okay, and it's a very small magnitude, but slowly we'll be expanding this to 100 kilowatts in future. All right, so I'll go to one more very quick application. Okay, so there are different applications that we have worked on. Today, the biggest challenge what we're facing is the kind of, what kind of inertial responses because of wind generations. Because in Indian power grid, not necessarily the PV, but slowly we will be capturing a lot of wind energy into the grid. Okay. So you can refer one of our latest IEEE transition on power system that is on 2020 last year, which talks about synergetic frequency regulation control mechanism for wind turbines with optimal pitch dynamics. So this is one of the very good application on microgrid that you can practice. And then we had actually one more application we are working on, actually demand side management. So what we have realized, as I told you in the past, the peak energy, during the peak energy, lot of renewable energy, they are not available to you. So the peak energy need to be stored. So instead of talking about electric vehicles here, I am representing as storage devices. Okay. And then these storage devices can be translated into electric vehicles. So what we are recommending, because you have a peak and off-peak load profile. So during the off-peak hours, I can charge my storage devices and I can discharge those storage devices during my peak hours. Okay. Or indirectly, I can connect my electric vehicles for charging during off-peak hours. How it can be done? That is the role of a smart grid engineer. But conceptualized way is that if I can charge my electric vehicle during off-peak hours, if I can discharge them if required during peak hours, if available, then I can reduce my peak requirement. So one way I put a lot of generation to be free from peak energy deficit. Another way, I can engage my thousands of electric vehicles or millions of electric vehicles on road to help the grid to reduce the peak energy requirement by discharging during peak hours. And that process, either you can call it a demand response or you can call it a demand side management program. And this is how actually we worked on. And finally, this article published in IEEE Transitions on Power System again in 2016, and where we, applied different logic for electric vehicle or storage, we can say. At that time, we have not named it electric vehicle, we named it battery storage. And we said that, the demand response activity can be carried out automatically through a two-layer smart meter arrangement, where the electric vehicle will be charged based on the wishes of the utility. So utility, all of you, please try to understand the structure. So you'll be very comfortable and happy here. Now the utility knows when there is peak and when there is off peak. We really do not know at home. Okay. So utility can know the peak and off peak hours. And based on the off peak and peak hours, utility can control my electric vehicle charging points. Utility can control the electric vehicle charging point, which has been controlled by my smart meter. So there is a DSM controller which is sitting on my charging point of the electric vehicle. So I do have electric vehicle. In that plug, there is a controller, DSM controller, which is sitting there on the charging point and which is remotely controlled. So my utility, the moment realize we are at peak hours, it will not allow your vehicle to get charged. Only during off-peak hours, it will be charged. So you plug it and leave it. In the whole day, your vehicle will be charged as and when you experience off-peak hours. And that you cannot go and do it, okay? The utility can do it. So we are proposing two different level of communications. There is a Zigbee communication for smart meter or your smart meter to electric vehicle charging point in your parking lot. And there is a GPRS communication between your smart meter to the utility. Okay, this is a wonderful work being very well appreciated in 2016. And now one thing actually by doing that, by simulating that activity, what we have realized, there is a lot of peak energy deficit. So either you name it electric vehicle, either you name it storage, okay, either you name it demand response. By doing such activity, one can experience minimum 10% and maximum 20% peak load reduction. And you see, all of you please try to understand what the blue curve is basically the load curve, the daily load curve of the utility. And the red curve is the desired load curve. The red one is the desired load. What do you mean by desired? Desired means whenever there is a peak, you want it to be off peak because you do not want peak, okay? So you want it to be reduced. Similarly, when there is a off peak, you want it to be more. So the red one will be my targeted load curve. You have a natural load curve and you like to shuffle it. You come from peak to off peak and off peak to peak. That you like to do it. So your targeted one. So if you do it, if you follow this process, finally you land up with a load curve, which is the green one, which may not be straight, but certainly one thing is true, that the green one is less than the original load curve, okay, in the process. So all of you please try to understand. So when you have a targeted load curve, in the process of achieving the targeted load curve, you arrive with a green load curve, green color load curve, and that load curve will be having less peak compared to your original. So how I have achieved less load, less peak? That means I might have shifted some of the loads to other powers. I might have actually discharged some of my battery energy available during peak hours. Okay. And similarly, in the off peak hours, I have actually, uplifted. So the process I'm not getting into detail here, but the load curve can be made flattened. That's what people are talking about, flat load curve, which is not exactly flat, but which is, reasonably flat compared to my original load curves. Okay. So this is another example where you can focus on. The first one is DFIC. The second one is your DSM. And I will also talk about a very interesting application that most of you may not be knowing about, is especially for electric vehicle applications, is a demand response at distribution or community level. You have a large apartment. How do you optimize your own energy sources? Because a community where you have a diesel generator, we have electric vehicles, we have solar PV on the rooftop, we have the main grid. Okay. So in that process, we have actually created a very interesting algorithm. And this is the transaction which has been published in 2019, just 1 year old. So we are actually scheduling the AC/DC residential microgrid. So this is basically a mixture of my 2016 work and some addition in 2019. So what I'm proposing here, you could see a lot of data handling, at the right hand side and the grid at the left hand side. So we need to generate an optimal command based on which my demand response activity will be carried out. Okay, and that response will be a price driven response. So I'm not saying that you shift your electric vehicle charging, but I'm also saying that my monthly bill has to be less. Okay, if there is no financial incentive, people may not be interested. So as you could see, there is a grid operator, distribution transformer, and then you have the complete grid of an apartment, of a community, and they are actually getting signal from the home data acquisition system. And that home data acquisition system is getting data from energy management devices. And through a smart meter, all the devices can be controlled. Okay, so this is a wonderful article. All of you, please have a look. And if you feel comfortable, you can also start continuing working in this area, which is very interesting. And you could also see the electric vehicles are in place. Okay, so today's FDP program is exactly suits what we are talking about. Perhaps I've chosen some of my research area that matches to the FDP. And these are the solutions. And then there is one more application which has been published in 2018, IEEE Transition on Smart Grid. And this is a very simple but wonderful piece of work. And perhaps this is a practical one implemented in the lab with both grid integrated and islanded mode of operation. We have visualized in real time. So this is the first time we got a success with a 5 kilowatt system. It's very simple. All of you, please have a look. We have a utility grid, and then we have a DC bus because it's a DC microgrid, and then we have DC loads, right? And then we have different type of sources. So we have mainly the battery and PV, ultra capacitor for spikes, but mainly we have battery and PV panels. The control logic, we have solved this problem using RTDS with most of the physical devices. The controller was sitting inside the RTDS and the devices were physically present outside the RTDS. And we had a power amplifier also for PHL expansion. Now, what I wanted to tell you here, that logic is, please try to utilize all your PV solar, okay? And once you complete all your utilization, if there is an excess, then you can charge your battery. And if still if it is off-load, off-peak hours, if it is peak hour, then you discharge your battery and then try to get some power from the main grid. And if that is also not possible, then you try to curtail some of your loads. So what is the advantage of doing this? All of you, please try to understand. The Hughes philosophy and all my applications that I'm talking about from 2016, 17, 18, 19, 20, they're all interconnected. Very interesting philosophy. Now, in the past, I told you that because of storage charging and discharging pattern, I can carry out demand response and help my national grid to experience reduction in my peak requirement. The same thing I'm doing here in a practical and physical way. So if I able to utilize my own energy, okay, because my target is not to withdraw power from the main grid during the peak hour, though I have not been paid any money for that, but that is my goal. I do not want to draw any power from my grid during peak hours. So because there are millions of microgrids, if all of them try to help the nation in this fashion, then the nation will not experience any peak energy deficit. So all my fellow friends residing in rural villages will be able to celebrate Diwali. That is the main philosophy for last 20 years. Okay. So here what I want that, please try to manage yourself within your DC or AC microgrid, whatever it is. Only when you are extremely shortage of power, then only try to draw power from the main grid. But if it is an off-peak hour, when the grid has excess power, then please charge your battery during off-peak hours also. And then discharge or utilize during peak hours using that battery instead of drawing from the main grid. And this battery could be electric vehicle to me. Okay. So, I mean, the same problem can be converted to another research problem by saying that a DC microgrid architecture with electric vehicle for nation's peak energy deficit. What a wonderful problem. Rajiv, sounds good?
Yes, sir.
Excellent.
And even it will be helpful like for the houses, residential buildings, where we
yes.
have rooftop panels, and if we have the electrical vehicles over there, that will reduce
Correct.
the burden on the distribution transformers, etc.
Correct. And then, but one more important thing, whenever we solve these problems, we need, some algorithm for loss calculation. And in that process, we realize, so we need a load flow solution to know the losses, voltage solution of the network. Either it is a DC microgrid or AC microgrid. So we are comfortable with actually Newton-Raphson, Gauss-Seidel in our graduate level, but that is not going to help for your microgrid structure. So we need to have new innovation load flow algorithms, okay, based on which I can calculate the losses and based on which I can design my control algorithm for the power mismatch. Okay, the cable loss need to be calculated. So for that,
Sir, I have one query.
just give me five minutes and then we'll take up your questions. Is it okay?
Sure. Thank you.
Or you can ask me better because I don't know, the time may fly. Please go ahead.
You can continue. Sorry, I'll ask in the last.
Okay. Thank you. Yes. So to do that, we have also developed a AC/DC load flow algorithm. This article has been published in 2019, IEEE Transition on Industrial Informatics. A wonderful algorithm for AC/DC load flow. And unfortunately, and this is not available in any textbook, okay? And this is working well, but it needs to be validated more to make it as a logic. So if you could see that, the orange one is my AC systems, and, and then I have a DC grid pockets, and then I have AC grid pockets. So you have the main substation, and then there are three clusters, and one of them is AC microgrid cluster, and the other two are actually DC microgrid cluster. And for that, actually, we try to solve the voltage solution so that for AC/DC microgrid, one can certainly obtain the voltage solution of the network. And I think now we are almost coming to an end. And this is my small laboratory. All of you can have a look. And as you could see that, the right side is the DC microgrid, and the left side is the AC microgrid. And this is the power amplifier for the DC microgrid. And this is the power amplifier for the AC microgrid. Then we have 6 rack RTDs. So this is the AC/DC microgrid capability of close to 25 kilowatt connected to the grid and its operation. And there are a lot of new thought process how we can take this to a national level. So the plan is actually to connect a 400 kV bus at a particular location, that is Haridwar. We are selecting now, and then I can have physical AC/DC microgrid connected to the bus, and rest of the bus will be simulated inside. So I can simulate the whole India network with a assumption that what percentage of renewable energy can be integrated. And if you have millions of microgrid in this country, what are the challenges? and up to what extent the peak energy requirement can be reduced with help of an optimal smart grid or microgrid operation at national level, and which has been grid integrated. So a lot of things happening, and then there's one more work on 2020, and a lot of things. This sort of time, as I told you, I can sleep for more than 8 to 10 hours, but still you can read all my publications. You can understand. Because my research work is mainly Indian focus, where I like to do something for Indian grid at the end of the day. And so they are actually of different things, not what you see in conventional literatures. So these are the reasonable publications you can refer to. And with this, I'm coming to an end. Thank you all for wonderful questions hearing. And once again, thank you all. I'll be happy to take a couple of questions if you have in mind. Rajiv, over to you.
Subho, could you discuss the questions with sir?
Sir, a very good afternoon to you. So it was a very insightful lecture. We had listened to you, and we had taken note of very important challenges that we are facing in our society, and through electrical power grid, how to stabilize it. So, sir, I have noted down some questions related to it. First question is that most of the forecasting techniques that we use for our research work, like ANN, that we can predict the we can predict the amount of generation side we can predict, but whenever we come to the load part, that there may be very variation, as well as there is always a possibility that new technologies are coming, like LEDs, through which the load is being reduced. So how to overcome this problem? That you have also mentioned that we can use DSM for that. Yes, sir. Sir, you are not audible, I think.
Am I audible now?
Yes, sir.
Yes, yes. Because generation load forecasting, especially for renewable generation forecasting, is more challenging compared to the load forecasting. The reason being, the weather. Suddenly there will be rain, suddenly there will be, kind of clouds. So predicting solar is certainly a challenge for anyone. Okay? But about the load, I don't think so there is any challenge, because if you see the overall pockets, because you are not taking any individual customer's prediction here. Load means load at actually 400 kV substation. So where all the loads are actually accumulated. Okay. And hence the error at 400 kV will be certainly very, very minimal. One can easily predict based on the customer's behavior. However, if you do the prediction at 11 kV substation, that will be a challenge. That will be a challenge, no doubt. But if you take the cluster of 100 of 11 kV substations and predict, then plus minus actually will be compensated. Yeah.
The second question is that how to choose battery size or storage size for a microgrid, means whenever it is connected.
Okay, we have recently completed this work. There are a couple of objectives you have to define. There are two important objectives one is to take. Because of the storage, how your voltage profile in the distribution microgrid is going to behave. That could be one objective. Second could be the loss reduction of the distribution. Okay, so with these two objective functions, if you optimize, you can certainly find the location and its sizes.
Yes, sir. And third question is that how to increase the share of RE. That also, I think there will be a scope that if we consider wave energy sources like that, and ocean thermal energy.
I agree, they are all theoretical, but let us be practical. Let us capture the maximum wind and solar available in this country. That should be the main target. Okay, And parallelly, we can do for research sake of research. But if you are really looking for some real-time implementation, focus on wind and solar and try to capture as maximum as possible for the country. And once the country overcomes the peak, like United States or Europe, when we have energy for all, then we can experiment with new things. All right?
Yes.
Thank you very much. So, any other questions?
Any other questions from participants?
Yeah, one or two questions we can take up.
One or
We have, our time is over, but still we can take one question. There are so many questions in the chat box. I think if someone can.
One question is that, sir, means distribution reforms after penetration of high level of EVs, not only EVs, renewable energy systems will be there. So, how to reform the distribution system for that?
We need to have a market, which is, I'm not comfortable by saying, unfortunately, our country do not have a market-based distribution system, or I can say a distribution system operator, DSO mechanism. Right. So we are awaiting for the first DSO to be launched in this country in next 6 months to 1 year time. Okay. And whereas actually we will be very surprised, some countries in Europe do have hundreds of DSOs, but such a large country do not have a single DSO, because the complications in Indian distribution system is something different, which is not as simple as developed nations in Western countries. So we are very careful. We are working on that, and probably in next 6 months to 1 year time, probably a white paper or a guidelines or some announcement has to come on a new first DSO of this country.
Sir, could you stop the slide sharing?
Okay, I will do that. Just a minute. What I have to do?
Sir, with this, we want to.
Yeah, I will exit. So thank you very much. Just a minute.
Sir, actually, I want to
there will
share
be-
something. Just please stop sharing your screen.
Okay, I have
there
done
will
that.
be a vote of
Yeah.
thanks.
Okay.
The faculty development program is an important initiative by the AICTE Training and Learning Academy. It will enlarge our scope for further research and development. The FDP on microgrid opportunities, renewable energy resources, and electric vehicles is jointly organized with the Dayalbagh Education Institute, scheduled from 5th to 9th of July. This is the second FDP of its kind due to this pandemic situation. So I like to thank Professor N.P. Padhy from Electrical Engineering Department of IIT Roorkee. He had enlightened us through his insightful talk on the AC/DC microgrid. Firstly, he had discussed about the challenges and remedies. Also, he had carefully addressed the remedies, and we will get some important points to do our research. There are some notable points are demand side management and electric vehicle as an alternative storage, like that. So thank you, sir, for delivering such a nice lecture on the topic. Thank you, sir.
My pleasure, and I wish very good luck to all of you. I'm very excited to meet all my colleagues today in such a wonderful forum, and I'm very sure that I haven't bored anyone for such long talk, and looking forward to see you all, and wish you very good luck in future. Thank you. Namaskar.
Thank you, sir.
Sir, please accept our one e-memento from our site, and thank you very much.
Thank you.
Being with us.
Thank you very much. Thank you. I accepted. Yeah.
Thank you, sir.
Thank you.